Hi, my name is Jamal Ashraf, and we're going to talk about the two sorting algorithms. I want to start with the selection sort. Uh, so selection sort is going to start with the first element. It's going to search the rest of the list or array and find the smallest one, and then it's going to swap. So it's going to start with the first one. It's going to look for the smallest one. It's going to swap. Then it's go to the next one. It's going to do the same procedure, and it's going to keep going until we are end of the list. So this is my list. I'm going to go through it. I'm going to find the smallest one in the list, which is 5. Then I swap 5 with 11. Then I start with 9, and I go look for the rest of the list. After 9, I find the smallest one in there, which is the 9 itself. Then I swap it. And then I go on 17. I look for 11 and 12. 11 is the smallest one. I swap it 17. And then I do the last one, comparing 17 and 12, and 12 is the smallest one, and that's the way we're going to get the sort, and we are done because the length right now is 1. We don't want to go after that. So that's basically called the selection sort. So the programming part of it is we're going to start with so the first part of this is we're creating a function for selection sort. We're going to go through the whole list. We start from beginning, go to the whole list, and then we're going to find the minimum position. We're going to create a function to create our minimum position. We are starting with the value that we have, and we're going all the way to I, and then we're going to find the minimum position, and then we're going to start our swap. So we're going to put one of them in the temp, and we go the second one and the first one, and then temp to the second. That's the swapping. So for finding the minimum position, we go through the list, and then we're going to have the starting position where we are starting. And if you remember in the previous one, we had the I, that would be our starting position. So it's going to be going to set it to what we have, and then we're going to go from a start plus 1 to the length of the values that we have, and then we're going to check to see if this value is less than my starting point, and then we're going to return the position for the minimum. So we are looking for the position minimum, and this function is going to return the minimum position. So we have that class that we created for a selection sort. We're going to bring the function of selection sort from the selection sort file here. And we also want to bring the random number generator. We're going to get the n for 20. You can ask the user how many elements do they want. We're going to create an empty list, and then we're going to create a number between 1 and 100. And we're going to put it in this values list. We're going to print it first. So the first one is going to be the unsorted list. We're going to call the selection sort with this one, and then we print it again. So that's the way we are calling our selection sort. Now we want to see how this is performing. So we can do this in multiple ways. One of them is to find the time. Of course, the time of taking a function to run or a program to run is different from computer to computer. That we have faster computer, a slower computer, but we can get some idea how is it going to work. So we do have this time library, and it has a time function that's going to give us a digit. That digit has started from January 1, 1970, and it's going to click for every second. That's basically for every machine. So we have that in every machine. So what we're going to do is we're going to start the time. We're going to get the time before we start our function, and then we're going to get the time after we done with the function. We deduct them, and we're going to calculate how long it's going to take to do this. So we are going to be doing, doing our import of random and selection. We're going to do our import for the time, and now before we call our selection sort, we're going to get the time. Remember, this is a time that is going to be, every machine has that, and it's per click or second. It's just going to keep adding to the number. And then we're going to get the end time after it. We deduct them from each other, and then we're going to find the difference. So when we run this one for the size of 10,000, it takes us about 9.4 seconds to do it. So this is the selection sort. We're going to check the different numbers. So we don't care much for the fraction of a second. For 10,000, it's going to take us 9, 20, 38, 30,000, 85, and so on and so forth. So we are testing for different sizes of the list. So if we graph this for the visual purpose, that would be the graph for this selection sort. And of course, this was done with the publisher on this kind of machine. So another way of looking at this is to find how many times we are visiting, and we're going to count the visiting time. So you calculate your cost based on how many times you visit each element. So in this case, to find the smallest, we're going to visit n elements, this whole thing, because remember, we're going to look at the first one, and then we're going to visit each one of them to find the smallest one. So it's going to be element plus 2 visits for swap. So we're going to go through the whole list, and when we find the smallest one, we're going to swap. So it's going to be basically n plus 2. To find the next one, then we don't have the whole n, we have n minus 1, and that 2 visit is going to be there all the time. The swapping is going to happen all the time. And it's going to keep going like that. So n minus 2, n minus 3, all the way through the whole list. So if we put those in an equation, so it's going to be n plus 2, n minus 1 plus 2, n minus 2 plus 2, and so on all the way to the end. Remember, the last 2, you just swap them. So this can be simplified as n squared divided by 2 plus 5n divided by 2 minus 3. And when we are calculating these things, we are going to be looking at the high end of it. So basically 5n divided by 3 minus 3 is very small comparing to n squared divided by 2. So we're going to ignore 5n divided by 2 minus 3. We're going to, and also n squared minus 2, we can basically half of it doesn't matter. It's going to cancel out with comparing ratio. So we're going to end up with n squared. So that's the way we're coming up with a notation called big O notation. And that's the way we're going to calculate the number of visits for the algorithm. and we're going to call it big O n square. That means what? Every time I increase my size by 2, my big O n square is going to be multiplied by 4. And of course, from the math part of it is function of n is a big O of g of n. That expresses that f grows no faster than g. Some math problems here. So basically what we're doing is we're going to locate the fastest growing term and ignore the constant coefficient. That's the way we're coming up with a big O notation. So in this case, for selection sort, the best case is going to be big O n square. The average case is going to be also big O n square. And the worst case is going to be also O n square. So it doesn't matter where how your list is. Basically, it's going to take big O n square. From the space complexity is O1, meaning that if I have a list or array, I am not going to need any more room in the memory. That's the only thing I'm working with. So we are not adding anything to it. So with the next merge, we see that we might need extra space to do it. So this was for the selection sort. I'm going to stop this one right here, and then we're going to come back for the other